Hello and welcome to Inductors Part II. At the end of the last video, we began to talk about the phenomenon of inductance and how that when we have a wire and we have current flowing through the wire, when the current first starts to flow, let's say in a DC circuit in a given direction, a magnetic field begins to expand outward from the center of the conductor and eventually reaches a maximum or stable value as it rotates around the conductor or the wire. Now, in a DC circuit, this phenomenon isn't particularly useful in most cases, but in an AC circuit, what happens to the current? And just a quick review here, we talked about how in a let's see if I can find it. I don't have the sheet, but in an AC circuit, as the voltage is continually changing, going to its maximum in one direction and then going back to zero, and then going to a maximum in another direction, the current is also doing the same thing. It's going reaching a maximum in one direction, then it decreases back down to zero, then it increases to a maximum with an opposite polarity, and then decreases back down to zero again, and that is one cycle. And remember that the number of cycles per second, or in other words, the number of time that we have a rotation of 360 degrees of our conductor moving in the generator inside of the magnetic field, the number of cycles per second is measured in hertz. So a signal that changes its polarity 1,000 times, in other words, or has this cycle of going to a peak positive voltage or current and then a peak negative voltage and then back to zero. If it does that 1,000 times a second, then it has a frequency of 1,000 hertz. Now, we also want to remember that when we have this expanding magnetic field, as it moves out from the center of the conductor, it actually the lines of magnetic flux actually cross over through or cut through the conductor itself, and what happens? This induces a voltage in the conductor, and that voltage is always opposite of or in opposition to the source voltage. So we can take advantage of this by taking our wire and wrapping it into a coil, so that we have if you've got a bunch of turns of wire that are right next to each other, that means that as that magnetic field expands outward, that it crosses through all of those the bits of wire in the conductor, and it creates a whole lot of induction. There's a lot of induction, or a bigger induced voltage in there. And remember, in an AC circuit, because the current is continually changing directions, this magnetic field is continually expanding and collapsing, and that's inducing a voltage each time that it does that. Okay? We talked about how that when you have a coil in a circuit and it induces a voltage, that voltage is always an opposition or has an opposite polarity to the source voltage. So if this line right here, this red line, represents our source voltage, and here it's at a peak, then the induced voltage, the voltage that's induced by the coil, is going to have its peak in the negative. It has an opposite polarity, and it opposes the source or applied voltage in the circuit. Now we can use this as a current limiting factor if we want to. Let's say that I want to make a circuit that doesn't short out the minute I plug it in, but all I have is a bunch of wire, and I want to connect this wire to the voltage source at the wall of 120 volts with the RMS value. Well, if I don't do something with that wire, there's really no opposition to current flow, or it may be 0.01 ohms of resistance. Well, you divide 120. In fact, we can do that right now. Let's So I have my calculator here. We can divide that by 0.01, and that represents just the resistance of the wire. This is a hypothetical. I divide that, and I have 12,000 amps of current that's trying to flow through my wire. That's going to heat the wire up very fast. It's going to short out and burn out. So what can I do if I don't have any resistors or loads to put into my circuit to limit current flow? Well, one thing I can do is I can sit down and wrap the wire up and make a coil with it. And when I do that, those turns of wire that are close to each other, if it's provided that I'm dealing with an AC voltage, every time the current increases to its positive value or positive peak value, that's going to cause this magnetic field to expand, and it's going to cut through all of those turns of the wire and induce a counter voltage. When the current drops back down to 0 and then begins to go in the other direction, that field will collapse, and then it will expand again as the current moves to its peak value in the negative or opposite direction. And that's going to induce a huge counter EMF that's going to oppose the flow of current, and it's going to have the same effect essentially as if I had put resistors into my circuit. There are a couple of big differences though between a resistor and using a coil in a circuit. For one thing, what causes the coil to have this induced counter EMF, this counter voltage that opposes the flow of current? Well, it's the change of the direction and flow of the source voltage. So if I have a really low frequency, that's not going to generate nearly as much counter EMF or counter voltage as if I have a really high frequency where the current's changing direction thousands of times per second. What are some other things that could affect the reactance? And here, by the way, when we're talking about induction and we're talking about using induction to oppose current flow in a circuit, that is actually referred to as inductive reactance. Although it's measured in ohms just like resistance, and it has the same basic effect on a circuit. Well, there are a couple of other things that can affect the inductance of a coil. One thing has to do with the number of turns. If I want my coil to have more inductance, if I want it to have stronger opposition to the flow of current in the circuit, then I just make more turns in the wire. In other words, I make a bigger coil. The other thing that can affect it, there's actually a lot of things. I'm not going to cover all of them because unless you're wanting to become an engineer, some of these things aren't necessarily that important. The other thing that could affect the inductance of a coil is how close the turns of the coil are to each other. The closer they are generally, the higher the inductance value. Okay. You can also take a magnetic core and you can put it in the center in the coil, and that will also direct concentrate the magnetic flux lines, and that will ultimately also increase the inductance of the coil. So there's some things that we can physically do to the coil itself to increase its inductance value. Inductance, by the way, is measured in a quantity referred to as henries. And the larger the inductance, the more opposition to current flow that you can get out of the coil. We talked about the other thing that affects the ability of a coil to oppose current flow, to limit the current flow in a circuit, and that has to do with frequency. So let's take a look at a formula that expresses this relationship. This formula right here, X sub of L, is basically the same thing as resistance in a DC circuit. This stands for represents inductive reactance, and we can find that value measured in ohms, just like with resistance, by using the following formula. We're going to take 2 times pi. This is the motion aspect of it, because remember, we're talking about circular motion. We're talking about how often it changes polarity. And then we also have the time factor, which is represented by the letter F, or frequency. And then finally, the L is the inductance value. And remember that the inductance is measured in henries. So let's take a circuit. Here's my circuit. I had no resistors, and I wanted to plug the wires straight into the wall and tap into that 120 volts of potential, but I didn't have any resistors. I wouldn't recommend this, by the way. So what I did was I took the wire and I put a bunch of turns in the wire and made a coil out of it, and I did my calculations, and there's a lot of different calculations you can do to figure out what the inductance value is of the coil. But the big factors here, again, it has to do with the number of turns in the wire, how close those turns are one to another, and whether or not I use a core material, some type of a magnetic material that can also increase the inductance value. Anyway, let's say that I figure that up and it comes out to 8 henries. Well, we certainly don't want 12,000 amps flowing through our wire. That would burn it up in a hurry. So let's see how putting some turns in the wire and making a coil affects the current flow in the circuit. Let's plug in our formula. Okay, so I've redrawn the circuit here. It's kind of hard to see the whole page there, and now we're going to use the values that I have here to figure out what my opposition to current flow is, which is called inductive reactance. And just like resistance, this quantity is going to be measured in ohms. I take my 2 pi and I multiply that by the frequency. Now, what's the frequency of electricity coming out of the wall in the United States? Typically, it is 60 hertz. That means that it changes polarity and goes through a complete revolution 60 times a second. I believe in Europe it's 50 cycles per second, or 50 hertz, but in the United States it's generally 60 cycles per second, which we can refer to as 60 hertz. So I plug that into my formula, 2 times pi times 60 hertz, and then I put in my inductance value, which in this case is 0.8 henries. When I multiply that all out, I come up with an inductive reactance of 301.5 ohms. So now let's hook up our hook up our circuit to the wall, the power, and see what the current flow is now. We certainly don't want 12,000 amps flowing, which could have happened if we had a really low resistance in the wire and then we just decided to plug it in without any loads or resistors. And notice here in a purely inductive circuit where there are no resistors, I can actually use the Ohm's law and substitute the R with X sub L, or in other words, inductive reactance, to solve for my current. What I do is I take 120 volts, I divide that by the inductive reactance, in this case 301.5 ohms, and that gives me a current value of 0.398 amps. Well, 0.398 amps is a lot more manageable than 12,000 amps. That would certainly burn the wire up in a hurry. So we've seen how I can put a coil into a circuit, and by it interacting with the frequency of the AC signal, it can restrict current flow. And by the way, it does this because, let's go back to another diagram, and then we're going to increase the frequency and see what effect that has on our resistance or inductive reactance value. But if you notice right here, we have our source voltage, which peaks right here, then it goes back to 0, and then it peaks in the negative direction, and then it goes back to 0 again. Notice that the induced voltage, the voltage that is induced by my coil, is in direct opposition to the applied or source voltage. It opposes it. It's 180 degrees, if you will, out of phase. In other words, has an opposite polarity at this point in time, at this point in the cycle, 90 degrees, while my source voltage here has a positive, my induced voltage is negative. Well, my source voltage must first overcome this counter voltage, this counter EMF, before current flow. And what that does is causes a phase shift so that the current actually flows, it lags the voltage. In fact, in a purely inductive circuit, it lags the voltage by 90 degrees. Now, let's go back to the other diagram that I had, if I can find it. Let's see. Ooh, where is it? Let's go back to the other diagram. And this time, I'm not going to increase the inductance value. In other words, I'm not going to wrap any more turns in my coil. But what I am going to do is I'm going to, let's say that I had somehow the ability to double the frequency, the number of times that the current changes directions, so that I could make the power coming out of my wall, instead of it being a signal of 60 hertz or 60 cycles per second, it was now operating at 120 cycles per second or 120 hertz. Now, what's that going to do to the opposition to current flow in my circuit? Well, let's take a look at this. So using my formula, where is it? Now I'm going to take my formula, which is X sub of L equals 2 times pi times the frequency times the inductance value. I didn't change the inductance value. It still has an inductance of 0.8 henries, but I doubled the frequency. Now look what happens to my resistance, or my inductive reactance. Notice that where we had the lower frequency of 60 cycles a second, or 60 hertz, we came out with a reactance value of 301.5 ohms. Well, notice that when I double the frequency, that I essentially double the reactance value. Look at how it goes from 301 to 603.185 ohms. So if I want to increase the reactance of the coil, the inductive reactance, to the flow of current, one way that I can do that is I can increase the frequency. Well, we take this new value and we plug it back into my formula. And so now I'm trying to find the current flow, so I use the 120 volts. I divide that by the new inductive reactance value of 603.185, and I now come out with a current of 0.199 amps, which is substantially less than the value of 0.398. In fact, I've practically cut the current flow in half. So that's how that inductive reactance works in an AC circuit. It opposes changes in current, or it limits the flow of current in the circuit, and it does this by inducing a voltage which is always opposite in polarity to the source voltage. It's a really interesting concept, and it's used in so many different ways, not only to limit current flow, but it's used in communications and many other areas, and many of the little gadgets and devices that we have in modern electronics gadgets. So that's inductive reactance, and that's how a coil works in a circuit. Now we're going to continue with this in the next video, I guess would be Inductors Part III, and we're going to have to add some little bit of more complicated, although not too bad, math. But what we're going to do is we're going to stick our coil in, and then we're going to put a resistor in series with that. It's actually going to change our phase angle a little bit, so we're going to have to use some different approaches to figuring out what our total impedance or resistance value is. So I hope you'll join me next time in the next video so we can talk about LR circuits, is what they're called.